Hey, welcome to Ones and Zeros. My name's Ben, and today we'll be looking at part 11 of our Discovering STM32 series. Only a couple of seconds in, and I already can't talk. We're doing great. So let's just fix up our headphones a bit. Hair doesn't want to behave itself today. All right, cool. So part 11 of Discovering STM32. We'll be working with our STM32F769I Discovery board, which is this guy here. So over the last 5 parts in this series, we've been looking at getting the LCD screen up and running. So getting our LCD, LTDC peripheral and DSI peripheral drivers done, getting all of that up and running, building a basic rendering engine and stuff for it, and then getting it to the point where we can draw various lines and simple shapes and text and things to the screen, as we can see there. So just carrying on from our last episode. In this particular episode, we are going to be looking at getting the touch controller up and running so that we can actually start to make use of the capacitive touchscreen on this device, including giving us access to a bit of data as to bits of information we can use when we go to start developing the user interface. So things like if you touch the screen and then drag your finger, being able to track the movement and how far your fingers moved, things like that, or being able to differentiate between a single tap on the screen or tapping and holding your finger down for a certain period of time, in order to give us different options depending on how we interact with the screen. This particular screen and the touch controller that we are using is capable of doing multi-touch as well, so you can get it to track multiple fingers at the same time. However, we're not going to be utilizing that simply because it is quite a small screen, so things like gestures where you might be pinching to zoom, things like that, aren't really required for the sort of tasks that we're going to be using this guy for. So headphones keep wanting to fall off tonight. Alright, so the particular touch controller that this device uses is the FT6206, or in this case the FT6206 touchscreen controller from Focaltech, and we're communicating with this one via the I2C bus, which is why this episode's been a little delayed, because we did want to get the I2C driver sort of introductory video that we did in the STM32 basic series done first, because we will be using that driver to communicate with this particular chip. There's not a whole lot in the documentation for this one. Unfortunately, this is the only document that I can find for this guy online, and I did have a look for a newer version, but this particular one doesn't even go through and list things like I2C addresses or iSquaredC addresses and things like that. It does talk about the interface itself, but not the best written piece of documentation I've come across. Thankfully, that sort of information was available in the code provided by ST. So bits and pieces of that I was able to pull across quite a while ago when I initially wrote the first driver for this touchscreen controller. So that was about 4 or 5 years ago now. And one of the things that I have noticed is initially back then I was working with the STM32F769I Disco boards, so it has an O at the end, whereas the current generation is the Disc 1 board. And they are basically identical. However, the iSquaredC address for the touch controller is different between the two boards, so we actually need to check which address the touch controller is communicating on, so that we know sort of which address we need to use for future communication. So that's something that we'll do when we go through and actually get the device initialized. And you will notice if we jump back to our other camera, So we can see this is one of the original boards, so it's a Disco board. It's also got a green PCB, whereas the newer version still shows the same model number. However, we can see that it does have a blue PCB rather than the green one on the other device. So this is one of the newer boards. So in order to make the code compatible across both of those, we do need to do that bit of a check. So first things first, we are going to go through and start getting the driver written for that one. And then we'll get that implemented, which will involve getting the iSquaredC set up, and then passing a pointer to the iSquaredC driver to the touch driver so that it can then communicate with the IC, get initialized, and we can start capturing some data, make sure that it's outputting data correctly, and then we're good to go from there. And then moving forward from that, we're going to start taking a look at getting some of the storage stuff sorted out for this device. So getting drivers written to be able to communicate with the 64 megabyte flash chip that is on the board, as well as getting the SD card driver, so the STM32F769I peripheral driver up and running so that we can start to communicate with SD card. And then once we've got all of the drivers sorted out, we're going to start building some layers on top of that, such as getting FATFS implemented so that we can use the FAT file system for both the SD card as well as for the flash if we want to do that as well. There's a few different options that we're going to look at, and we're going to try and make things a little bit universal, so no matter how you or I want to make use of the QuartzArk code, we can sort of tweak it to suit those particular needs. So let me just grab this guy here. And first things first, let's get some files created so that we can get the drivers done. Now I'm going to create a new folder in drivers, and we're going to call it QAD devices. We're going to use this one for situations where we're speaking to a particular device and it's not just, say, a universal peripheral, such as we've done for like GPIO or FMC or real-time clock, things like that. So in this case, this driver is specific to that focal tech IC. So we're going to pop it into this folder. And to make sure that that all behaves itself, we're going to jump into C++, C++ General, into our paths and symbols, and we're going to make sure that we get this chucked in as an include in here. Now that will go into here, and that will be QA drivers, might help if we use a slash, QAD FT6206, which is the particular IC that we will be using. So let's just rearrange these guys a little bit. That can go there. Actually, I'm going to want to change that in a second as well. So let's just rearrange this one, because it might help if we actually give that guy the right name. That should be devices. That's a bit better. Which has changed its ordering anyway, so we'll just fix that up. Off to a good start this evening. Alright. Apply that one. Yep. And let's create a couple of files in here. So this will be QAD FT6206.hpp. And we want QAD FT6206.cpp. And let's just grab our GPIO driver, which we'll copy the header from. Paste that in there. We're up to the 3rd of December. While I'm getting this done too, we have reached our first milestone of over 100 subscribers on YouTube. And as you might have heard me mention in some of our other videos, we are looking at doing a bit of a giveaway to one lucky person as a result of hitting that milestone. So keep an eye out for the next devlog, which will be coming out next week. So that'll be devlog number 4. That will have details on how to potentially get your hands on a bit of free stuff. So that will include a STM32F769I microcontroller, as well as a few additional bits and pieces. So a little blue pill board, plus some extras to go with that. So you've got some things to hook up to it and start playing around. And that one is compatible with the code that is up on our GitHub. So the particular Quartz Arc code for the blue pill board was developed for those particular devices. So let me just get the bug off my screen. That's a bit better. Let's get our prevent recursive inclusion done for the end of the file as well. Like so. Now, because we only have one of these ICs on the development board, we are going to go ahead and use a singleton class to get this driver set up. So similar to how we've gone through and actually set up the drivers previously, it's going to be a similar approach. There will be some slight differences, like we don't need an initialization structure to get this guy set up, which does make it a little bit simpler. Basically all we're going to do is hand it the pointer to the iSquaredC driver, and then it can just go from there and gather the touch data for us. So FT6206 Okay. Not sure if the coffee is working tonight, but that is okay. So there will be a few bits of information which we're going to have in here, but let's get our constructor out of the way first, and some of our singleton class specific stuff. I'm just going to pop that in like that for the moment. We're going to go through and delete our copy constructor and assignment operator so that we can't get more than one copy of the class due to us only having one device we want to be communicating with this driver. I will have some more videos in our Unearthing C++ series coming out shortly as well, one of which will be looking at classes and one which will be specifically looking at singleton classes, where we'll sort of go into a little bit more detail than I have during some of the STM32 videos. So keep an eye out for those if you want to learn a bit more about that sort of stuff. But basically just deleting the two things that are designed to allow that class to be copied in a situation where we'd allow for there to be multiple copies of the class. So that is that one. Now, in order to get access to this particular driver class, we're going to need a method to allow us to obtain a reference to it, which is what this guy is used for. So this will return a reference to a Q8E FT6206 class, and don't need to pass it anything. And we're declaring a static variable in there, which will grab hold of, because it's been declared static, it will grab hold of the only instance of that class that will exist, and then it will return it. So that's how we can get hold of that one. We'll also have some initialization methods, which we're going to come back and sort out shortly. And then we're going to have another private section down here, which will contain our implementation methods. similar to how we've approached that previously. So a few bits and pieces that we're going to have stored in our class. First up, we're going to look at, as I mentioned, there's two different addresses which we can be communicating with the IC on depending on which revision of this discovery board we're using. So we're going to create some constants in here, the first of which will be those two addresses. So let's copy those guys across, grab all of these guys and do this in one go. So a few constants. The first two will be the two addresses. This first one is the one used by the first revision board, and the second one is the one used by the disk 1 or the second revision of the board. We've got some register addresses for the registers inside the IC. So the ID register is the one that we're going to be reading during initialization in order to make sure that we are communicating correctly with the device. And then we've got other registers that we can access to be able to do things like reading touch data, checking whether or not there is actually a touch occurring, as well as controlling things like interrupts as well. Which we're not actually going to be using in the driver at this point. However, that is functionality we may go through and add later. The way we're going to be using the driver at this point is just to be polling it each time we go to render a frame in order to grab the most up-to-date touch data at that point. So similar to how we would approach it if we were working with a game engine. It's kind of the approach that we're going with there. Now I've also got this constant, which defines how long in milliseconds the threshold is in between just a simple single touch and actually what it will look at as a long touch, which is when you touch and hold. So in this case, 2.6 seconds. That can be adjusted to suit. That's just kind of what I find works for the way I like to go with things. And we've got a few variables which will be containing some of the data that we'll be storing in order for the driver to be able to process what we need. So first things first will be a pointer to the iSquaredC driver, and init state enum to store whether or not the driver is actually initialized. This address variable will be storing the address for the device. So when it goes through, it'll try and check the status register from both of these addresses. The one that gives a successful reply, it will then store that address in here so that that can then be used for reading touch data and things like that. So it doesn't have to keep checking which address is correct. Once it knows, it'll just keep using that address. Now, some of these we might actually change to Booleans. So these guys will be tracking whether or not there is actually currently a touch, whether there was a touch when we last checked. So between those two, we can actually tell whether it is the very start of a touch. So if there was no touch last time we checked and there is now, then that's the start of that event. If there isn't now, but there was the last time we checked, then that would denote the end of a touch, things like that. So that those guys are used for that. This event is similar to that in that it allows us to check whether or not there is actually an event of some description occurring. This one will store whether it's the start of a new touch, and this one will store if it's the end of a current touch. And this guy will store whether it is a long touch. So if we've held our finger down for more than our threshold value. So that's the data we're going to be looking at there. These guys help to be able to check whether or not we've exceeded that long touch threshold, as well as managing that stuff. And then we've got our coordinate data. So the current coordinates of where the touch is occurring on the screen, the coordinates for the last time we checked, how far that touch has moved. So if you've touched the screen and moved your finger, doesn't matter which direction, it will actually track how far that's moved since the last time we checked. And then we're also going to be storing the very first coordinates when you first put your finger down. So even if you then move your finger, it's going to keep track of those start X and Y coordinates so that we can refer back to those if we need to, depending on how we want to work with the particular element that our UI is detecting is being touched effectively. So I hope that kind of makes sense. So initialization methods, got a couple here, and we're going to do a little bit of copy and paste stuff here just to keep the things flowing a little bit better. So an initialization method which gets everything set up, and a deinitialization method which frees everything. As we've done fairly similarly, we'll have a processing method, which is effectively the method that gets called in order to gather the current touch data. This guy gets passed the amount of ticks that have passed in milliseconds since we previously checked the touch data, and you'll notice these guys are calling the implementation methods that we are yet to declare. Excuse me. There is a few data methods to be able to retrieve data from the driver so that the UI can actually gather all of that sort of stuff. So just to be able to get it to access the various bits of information we've got stored in here. The one additional one is this get touch within, which allows us to provide a start and end set of coordinates and check if the touch is occurring within those. So we're basically going, is that touch occurring within this particular area? And the reason why we have that is so that if the UI has, say, an icon on the screen and it wants to be able to go through and check, is that icon being touched, it can pass the top left and bottom right coordinates of that icon and get it to check whether or not we've got a touch occurring in there. And again, a few of these we are going to change to Booleans rather than using UN8Ts, simply because it's a little bit safer from the programming side of things, in that the compiler will sort of check that we're not using values that we shouldn't be using, similar to why we use enums effectively. So that is all of the ones we want there. We've got the guys to be able to retrieve the various different coordinates. So the current coordinates, how far we've moved since we last checked the touch data, as well as what the coordinates were at the start of the current touch. Now we've got to pop in our implementation methods as well, which we will be putting in the private section. Get some liquid, might be good. Let's just jump to that one for a sec. It's rather humid where I am at the moment, so the coffee is making things a little bit too warm, unfortunately. So we'll have the implementation method for our processing method, for our touch within method, and also a couple of sort of tool methods which we're going to be using. Change this guy to a Boolean, and the first one of those will be to confirm the address. So that will return either QA OK if it's found a device at one of those two addresses, or QA fail if it hasn't found a device on either of them, as well as a method we can use just to clear our data that we're storing in here, basically to all zeros, so that that's good to go for the start of the next touch or when we're initializing, things like that. So that basically describes those. Now there is a couple of things we're going to need to include in here, one of which will be our QAD iSquaredC.hpp, because it'll need to communicate with that driver. And we're also going to need, that will be QAT vector2 16, which is stored in the QAT vector.hpp file. So that is everything that we need in our header. So let's go and copy this stuff across to our source file. And I didn't fix that up either. So that will be, I'd actually make that FT6206 touch controller driver. And we'll fix that up in our header file as well. Need to get rid of these guys and that one. Need to fix this up here. Should be CPP, and we need to lastly include our QAD FT6206.hpp. Wonderful. Alright, so we are going to want our initialization methods first up. So our initialization method basically just goes through and first stores the handle to the I2C driver that's passed into this method. It first checks whether or not it's null. So if it's false, we know it's null. So it checks that it's not true, and if it is, then it returns QA fail to say I need a driver in order to be able to work. If it's not null, it will store it, and then it will go through and call the confirm address method in order to check that we do actually have a valid device on one of those two addresses, and also store which of those addresses we need to use for future communication. If it can't find a device on either of the two addresses, then it's going to return fail. We'll then go through and clear all of our data that we'll be using to track the touch states, things like that, and then set the driver state to show that it is currently initialized. And then our dinit method just basically goes through, checks that we are actually initialized, and then just sets the driver state to not initialized. So it's not actually making any changes there at all, other than that. Now, the one thing we are going to need to change is in our constructor, is we are going to initialize a couple of these members in here, just so that everything works correctly when the class is first created. So the two things that we're most worried about is m_i2c, or m_c i2c, which is our pointer to our driver. It'll help if we do that one correctly. So we're going to set that to null, and we are also going to set our init state to QA not initialized, like so. Everything else we're not too worried about, because that is all going to get sorted out when the driver is initialized, and none of that's going to be used until the driver is initialized anyway. So that is that one there. That's all good. That's our initialization and deinitialization methods. We are going to grab our processing method. Now, there's a bit of stuff going on in this one. It's probably the most complicated method of the whole driver. So let's get our indent sorted out there, and we'll run through what we're actually doing in here. Where are we? And we want that next line as well. That's better. All right. So first things first, we're going to store our what was in our current x and y into our last x and y, because at this point that will be from the last time we checked, and then we're going to set our current x and y to 0. Then we're going to check with the touch controller whether or not there is actually any touches occurring. And if the value we get back is greater than 0, we know there's at least one touch occurring. So if there's more than one touch, then we're going to go through and actually read the touch data from the touch1 register. So that will give us back the raw data for our X and Y coordinates, which we then unpack from those 4 bytes that we've received, and we store those into the raw X and raw Y uint16s that we've got there. So just because of the particular order that we receive those in, we're basically just switching the bytes around and also trimming them off so that they're 12-bit values rather than 16-bit values, because that's what we're actually getting back from the touch controller. We also need to flip the Y coordinate. So that means in order to be able to access this guy, we are going to need to pop in include QAD LCD? No, LTDC .hpp, which is this driver over here. So that's where that constant value is stored. So flipping the Y coordinate, creating a couple of temporary variables to store our X and Y values in. We're going through and actually checking our raw X and raw Y values against those 0 values. So that if we get a value that's not quite right, it's effectively going to fix that up for us. I will explain that a bit better in the commenting when that goes in. That will be up on GitHub. It's the best way I can explain it at the moment. Check that again as kind of a validity check that we're doing here. And as long as we pass all of that, then we're then going to check whether or not our X and Y values are within our screen coordinates. So if our X is greater than 800 because we've got an 800 pixel wide screen, or our Y is greater than 480 because we're 480 pixels high, then it's going to set num touch to 0 in order to basically say no, there wasn't any touches. And then we're going to store our current X and Y coordinates in our, we might actually change this up so that if it's only going to store those 2 values in our current X and Y if we have a valid bit of data there at that point. All right, so once we've got that data from the IC, which is basically what this is all doing, we can then go through and actually start processing that. Now, what we're going to do is, firstly, we're going to look at whether or not I'm just changing this up a little bit. So our value that stores whether there's a current touch that we were using the last time we checked for data will be stored in our last down variable. And then our current one will then be filled with whether or not there is a touch currently. So basically just checking Boolean whether num touch is greater than 0. And then we're going through and just checking whether or not it's a new event, the end of an event, or whether we are getting any sort of event whatsoever. So a new one checks that there was no touch last time we checked, but there is currently a touch. Whereas our end checks the opposite of that, so that there was a touch last time we checked, but there's not at the moment, which would signify that we've taken our finger off the screen, basically. Whereas our UData event basically stores whether we're currently touching the screen or not, either during the last time we checked or currently. So that kind of stores whether there is any sort of touch event happening at all, or whether we had our finger off the screen both this time and last time we checked for data. So apologies for the sweating. It's a little bit humid this evening. So in here, we're basically going through and checking if it's not a new event or the end of an event, then it's going to go through and process the data in here. So it's going to store any data for movement that has occurred in between the last time we checked for data and the current time. And it'll store that. It's going to increase the long count by the number of ticks that have occurred in milliseconds since the last time we checked for data. And then it is going to check whether or not it is a long touch by comparing whether or not the long count has exceeded the long touch threshold. Now, that, because we've changed that to a Boolean value, we can just check for that Boolean and it saves doing that extra bit of stuff there. So if it's a new or the... No, this one will be in the case of just the start or end of a touch. It'll set the move values to 0, because if it's the start of a touch or the end of a touch, then there's not going to be any movement in between the last time we checked and the current frame. Basically, it might refer to those as frames, might make it easier. So think of like frames per second in a computer game. We're going to check if it is not the end of a touch. So in this case, it'll be if it's the start of a touch, then we're going to set our long to false, and we're going to set our long count and our long pulse both to 0, so that we can start checking from the start of the touch whether or not that finger ends up getting held down for more than the period that defines it as being a long touch. And then if it is a new touch, then we're going to store our current X and Y coordinates into our start X and our start Y as well, so that we can keep track of what position was the start of when we first started touching the screen. Again, all of this code will be a bit better commented behind the scenes, and those comments will get updated to the code that's up on GitHub. Much like our previous videos, this code will be available up on GitHub from typically 10 minutes or so after the end of this stream. For those of you watching on YouTube, should already be up there by the time you are watching this. Last thing we're going to do in here for processing our data is check whether or not we've defined this as being a long touch. If it is, then this is where our long pulse value comes in. So effectively, with the way I implement the UI, I only want it to show up as being a long touch for one frame of that whole thing. It just makes the UI a little bit easier to implement, which is what we use our long pulse value for. That will be, fix these guys up as well, because we've changed those over to Booleans. So basically, if it is a long touch, then it's only going to register as being a long touch for the first frame that that long touch is occurring, in order to avoid the UI triggering multiple long touches. So again, that depending on how you implement the UI, you may or may not need that, but that's basically what that's doing for us. We're going to want the implementation for our touch within method, which is this guy here, which basically we hand it to vector2, so the start coordinate and the end coordinates, and then it goes through and checks whether or not the current touch coordinates, the X and Y, are within the start and end that we've defined. So basically allows us to check that whether we're touching inside of or outside of a rectangle area. So that's those guys, and then last couple of methods we need for the driver. So driver's nearly done. We might just fix the indenting on that guy and on this one while we're here, and on this bit of code. So basically we've got two result variables, one for each of the addresses, so for the A address and the B address. it's going to go through and try and read the status register of each of those. So the first one using the address from the earlier revision discovery board, the second one using from the second version of the board, and then it's going to go through and check if each of those match the MUID value, which is the value that we expect to get back from that ID register. So if A matches, then it'll store A's address into our address variable. If B matches, it'll store B's address in there. If it doesn't get a result from either of them, it'll return fail to let us know it hasn't been able to find a device on either of those addresses. But if that's successful, it will return QA OK to our initialization method. And lastly, we've got the method which we will be using just to be able to clear the data that is being used to be able to process the touch stuff. So let's change these ones that we have switched over to using a bool. We will change all of those to false instead of 0 so that we're doing all of that correctly. And that is the touch driver. So quite simple. Most of the stuff is done by this poll method that we've implemented here. We're not gathering that much data from the touch controller itself, just how many touches are occurring and the actual raw X and Y data, and then doing our bit of processing on that in order to allow us to check what's actually occurring. So that is that one there. Let's firstly, we'll include it in here. And we're also going to need to include our iSquaredC driver as well. And that will be FT6206.hpp, and let's just make sure that guy compiles. We have errors. We have errors in here. Wait. Oh no, we've done that. So what's it complaining about? Does not name a type. What's this guy? That one we can fix up pretty easily. So that should just be returning instance. What's the error we've got in here? Declaration doesn't match. Let's just check that against this one. We'll get rid of that for the moment. Aha, because this one should be returning a Boolean value, which means we need to modify that. Let's try building that and see. Still getting this particular error for this one. Aha. No, where are we misnamed it? Right there. Missing the FT. Of course it had to be something simple. The looks like it's going to build this time. Wonderful. All right, a couple of minor errors there, of course. So we're going to go down below where we're actually initializing our LCD and our random number generator real-time clock in main. We might actually modify this in here. We'll get rid of our real-time clock and random number generator stuff that we used from those particular videos. And we're going to want a touch update tick threshold, as we're going to be wanting to check the data, and we'll be doing that every second, so every 1000 milliseconds. And I'm going to want to change, so our processing loop is there. Get rid of that guy, and we're going to change this one to touch update ticks. And then let's call this update touch data. So you touch update ticks plus equals you ticks. If you touch update ticks is greater than or equal to QAFT touch update tick threshold, then we'll do this stuff in here. And if that has occurred, then we need to go through and go touch update ticks minus equals QAFT touch update tick thresholds. And we can do stuff we need to do in there for our processing loop. So let's get our initialization stuff done. Now it is I2C4, so there's 4 I2C or iSquaredC peripherals on this particular STM32 chip. We're going to be using I2C4, so that's used to both communicate with the touch driver itself, as well as for controlling the audio codec chip that is on the board. So basically going to be sharing that one I2C or iSquaredC device between the both of those. Make a note of that there as well. And that will be QAS I2C. And be a pointer to that one, and we're going to call this I2C system. Because it's the main I2C that's getting used on this particular device. Because we're using the FT6206 driver as a singleton class, we're not going to need to create a pointer for it because of how we actually access it as it being a singleton class, similar to what we do for our LCD system, things like that, how we access it using the name of the class itself followed by the 2 colons. Will be the way that we access that one. So we want to initialize that iSquaredC as well as initializing our FT6206 touch controller. Pop the comments in there for those, and then let's go through and get these guys set up. So to set up our iSquaredC, we first need to provide it with an init structure filled with the details of how that one's going to be set up. So telling it that we want to use I2C4, handing it the priorities we're going to be using for the IRQs, although the IRQs are not going to be used in this situation. The particular timing value in order for the iSquaredC peripheral to operate at the required clock rate. So that value will give us a clock rate that suits both the audio codec as well as the touch controller. We're using 7-bit addressing mode for both of those ICs, disabling dual addressing, general call, and no stretch mode. setting both own addresses to 0, and then setting the details for our clock GPIO pin and our data GPIO pin as needed there. That's that one. So we want to go through and actually create that driver class. Then we'll go through and get that one initialized. So we'll initialize that. If it initializes fine, if it fails, sorry, then we'll let it send out a message to say that it's failed. Turn on our red user LED to let us know there's an error occurring, as well as jumping into an infinite loop. And then we'll tell the I2C peripheral to start. So it's good to go, and output a message letting us know that that one has been initialized and started correctly. And then for our FT6206, it's basically just a matter of calling the init method from the singleton class and passing it a pointer to our I2C driver. Again, if it fails, send out a message letting us know, turning the red LED on and jumping into an infinite loop. If that's successful, then we'll send out a message letting us know that that has actually worked correctly. So we've got our temporary string there, so we can print out stuff during the processing loop, which is good. Let's just copy and paste this bit as well. So basically this one is going through and calling the poll method, as well as providing the amount of ticks that have occurred since the last time we called the poll method. It is creating some variables to store the current and the move values into, and then depending on whether it's the start of a touch, the end of a touch, whether a long touch has been triggered, or whether we've actually got our finger on the screen in general or not, then it's going to output that data specifically so that we can actually see it in the serial monitor. And as long as that's all working, then we might actually do a little bit of stuff just so that we can see how the calibration's working on the actual touch screen. So we'll look at getting it to draw a box on the screen at the particular position where we're touching it, so that we can make sure that that's actually working correctly as well. So, telling me that's not what I called it. Oh, that should be a QAD because it's a driver. That will be why we have that error. All right. Let's get that dumped onto our device. So jump over to this one. Just transferring that code now. So that has restarted. Green LEDs flashing down the bottom to let us know that it is running, and we don't have our red LED, which would be on the one on the left of where the green one's flashing, is not lit, so we don't have any errors. If we pull up our serial monitor, and we connect that guy, we can see that we're actually getting data there. And let's just restart this one. Make sure that our initialization sequence shows up correctly. So that's all initialized. We're getting no touches there. If we touch the screen, it's showing us the coordinates as well as the movement, things like that. And we can also see that it did show us that we got a long touch in there as well on that particular line. So just want to select that one for me, but right there. And it's registering the start and end of the touches correctly. because we're only updating this once a second, it's not giving us the clearest look at that, but that is working exactly how we need it to. So I'll disconnect that and clear the data for the moment. And let's go through and implement our last little test for this one. So let's go down past where it's actually outputting that stuff there. We might comment out this here, because in order to get things to show up smoothly on the screen, we're probably going to want to update slightly quicker than once a second. And so that we're not getting a ton of data being spat out serial, we're going to turn off the serial output for that one for the moment. By putting in 33 here, should give us about 30 frames a second, I believe. If we grab calculator, so 1000 divided by 30 gives us 33 in decimal. So 33 milliseconds will give us an update rate of 30 times a second, or 30 frames a second. Now we're going to want some LCD stuff in there, so go through and grab this bit. So we want to go through and clear both layers. Clear the top layer to all zeros. And then we are going to want to, might even just make this a bit easier. Do that so that we can access both of these side by side. I'm going to need to flip both of those layers. So I'll grab that there. Technically, because we're only going to be rendering to one layer, we don't actually need to clear both of them, but we're going to do it anyway because we are going to get plenty of performance out of this, so it's not going to matter too much. And then let's copy this stuff to draw a rectangle. We might make it black background and a white rectangle just so it shows up nice and clearly. And then we're going to need to get some coordinates sorted for this. So let us actually, we'll leave those as ints just in case we want to uncomment the serial stuff to debug at some point. And I'll leave all of that in there anyway. So we're going to go QAD FT6206, and that will be get move X. Which we're not actually going to be using at the moment, but it's going to allow me to clean up some of the code that we were using for serial while I'm here, just because I can't help myself. So FT6206 get start X, which means we don't actually need to be doing that inside these guys. Which then gets rid of a bunch of lines of code that don't really need to be there. Much neater. Alright, so in the case of drawing to the LCD, because we're going to be drawing a certain size square onto the LCD screen, we want to sort of trim the coordinates so that our square is not going to go off the edge of the screen effectively. We might do a 40 by 40, maybe. Might do an 80 by 80 sized rectangle or square. So if UX is less than 80, then ux will be equal to 80. Else, if ux is greater than, that'll be 719, because that's 800 minus 80. Which means that we're going to have a square that's, so we're going to go with half the square. So if the square is going to be 80, we want half of that, which will be 40, which will make that 759. Just want to try and make sure that that's actually going to be big enough for us to see as a bit of a demonstration. So, but if it is too small, we'll just come in and increase it. Uy equals 40, else if uy is greater than 439, then uy is equal to 439, which makes sure that it's not going to go off the edge of the screen. So this will be ux minus 40. Nope. We want ux, not yx. Uy minus 40. I'm going to go ux plus 40 and uy plus 40. Wonderful. FT6206 gets down, or if it's the end of a touch, then we will render that one, otherwise we won't. Like so. That all looks good. Trimming those coordinates, clearing the layers, drawing our rectangle if we're currently touching the screen, and then flipping them. Getting that done at 30 frames a second. Let's make sure that builds. Just not happy with those. Not sure why we are getting that result. That's how we were doing there. Aha. Okay. I'm trying to pass it a function pointer. That's not going to work. Need the parentheses in there. And we will get a few warnings for unused variables, no doubt. So we're not actually using either of the move variables at the moment, so we're getting warnings for that, and also for our temporary string here as well. That's fine. Let's dump that code onto our device. Getting that copied across, we can see our LED flashing. Currently nothing on the screen. Right, a little bit of weird behavior. Okay, that's not what we want. What have we done wrong? Let's jump back to that one. So firstly, we're getting that weird behavior with the top and the bottom of the box not being drawn in some situations, and then the fact that the coordinates are in the wrong spots. So why are we getting that? passing it the correct coordinates that we want there. Let's slow down our update rate. Let's go with 10 frames a second and some serial output so that we can debug that a little bit easier, and we'll see why it's doing that. Camera is misbehaving. So for some reason, let me check. Our processing loop. That's because we're grabbing the start coordinates of the touch and not the current coordinates. Made sense as soon as I saw the numbers. Let's dump that back over onto our device. We're going to keep our serial happening still, so that will come in handy. Now, something weird going on with the data. Let's make that square a bit bigger, because it'll make it a bit easier for you guys to see what I'm seeing. So let's double the size of that, so that'll be 719, 719, 80, 80 for, no, 399. 480 minus, or 479 minus 80 is 399. Let's pop that onto the screen. And let's pull up our serial monitor again. So on the left half of the screen, it's actually tracking quite well. I didn't change the stuff in here, that might help, in order to increase the size of the square. Let's try that. Okay. So again, it's behaving properly over on the left-hand side of the screen, and fairly accurately tracking the touch. But it's only working in certain areas. We have a weird thing happening with the data in that down the bottom of the screen it works further over to the right, whereas at the top of the screen, so there's something funky going on with our X and Y values getting mixed up somewhere. So let's have a bit of a look at that. So UX, UX, UI, UI. Those guys are correct, it's not in there. Let's see what we've got happening in serial. What values are we getting there? X is 17, 719, 382. So that's correct, which means it's got to be our renderer that's messing that up. Because the actual data from the touch controller is correct. There's something going on with the rectangle drawing method. X and Y, X and Y. Alright, so let's get rid of our vertical split on that. Let's chuck our LCD file over here. And where is draw rectangle? Right there. These guys are getting done correctly using uint32t, so it's not the top and the bottom are getting also messed up when we're over in that sort of forbidden area. It's almost a diagonal that it's working on. That might be one that I will figure out off stream, I think, because we know, at least in the area where it's behaving, that it is actually tracking correctly. We know that the touch data that we're getting is correct, so there's something wrong or weird going on with the renderer, and it's either got to be in the vector class or in the actual LCD class in our renderer method here. And it's probably right in front of me, but I'm not spotting it right at the moment. But that's fine, because I will figure that one out anyway. Pop that on my list of things to get fixed up. Glad I spotted that now rather than later. If you do come across any bugs in the QuartzArk code for any of the devices that we've put up there on GitHub, definitely reach out and let me know. I don't like having bugs in my code and would much rather go through and get those guys fixed up. Let's jump to this guy, because I think the other camera is being a bit of a dick at the moment. So that is our touch driver up and running, all working correctly. In the next episode of the Discovering STM32 series, as I mentioned earlier, we're going to start looking at some of the storage stuff, getting the last of our drivers up and running. And once we've got drivers out of the way, we're going to start building further systems and things on top of that, which will include, as I mentioned earlier, things like FATFS, so that we can actually get a file system and file manager implemented. We'll be looking at implementing a console system so that we can use the serial terminal or other methods to be able to send various commands to the device and get it to respond accordingly. We're also going to be doing stuff like getting the UI up and running, making sure that that all works correctly so that we can get the UI to basically works in such a way so that for various pages, for each of those we can define a set of things that are going to be displayed on that page. So for example, we can say, okay, we want an icon located at this location with this set of properties, and it's going to react in these various ways depending on how we interact with it or what's actually occurring. Which is quite a flexible system. It allows you to get UIs whipped up fairly quickly, modify them and stuff fairly quickly, and is the typical approach I use for most of the projects I work on, just because it's really quite flexible and allows us to have, you know, text, images, all of that sort of stuff. and some quite cool looking things, as you might see on this picture here. So that stuff on the screen is the very first version of that UI that I developed, and that's actually running some stuff for a synthesizer that I wrote for STM32 devices. So had my MIDI keyboard hooked up to a couple of H7s as well as one of the F7 Discovery boards, and all working together as a team to be able to provide cool digital synthesized audio, which is a project that we will actually be looking at once we get some of the further drivers and systems out of the road and we start to look at actual projects that we'll be doing with the various STM32 devices. We will also be looking at putting out another stream after I take a bit of a break, where we'll be looking at the first in our FPGA basic series. So we're going to start to get into a bit of the FPGA stuff as well. So keep an eye out for that. And to all of the new subscribers, a huge thank you to all of the people that have been watching the videos. It is really awesome to see some of the comments and things that are being left. So if you do like watching this stuff, please like and subscribe if you're on YouTube, or give us a follow if you're on Twitch. If you do want to get in touch, we do have the details right down there for our subreddit and our GitHub, Patreon, as well as our email address. The code from this video will be going up on GitHub in about 10 minutes or so. Bear in mind that there will be that particular bug which we've spotted, so maybe I'll give you the chance to try and find it if you're interested in doing that as well. And yeah, thank you very much for watching. Look forward to the next one. Thanks.